So it doesn't look like it's squashed, but it's four-dimensional. It's been squished, just like if you have a cube and you squish it, you can have those two squares connected I showed you earlier. This is like two cubes connected, basically a squished tesseract or projection. Alright, so next. I had a really stressful morning this day. So. Alright, yeah, that's what I meant to say. So here, we're going to use cross sections to visualize four-dimensional space. Now, just like many other things with this four-dimensional topic, since we can't see it directly, it's much easier to use two-dimensional examples. 2 to 3-dimensional examples instead of 3 to 4. So, I'm going to call this place Flatland, alright? Can you guys stop squabbling over this? Like, it's really annoying. Please, just stop, both of you. Babbling. Jack, just quit it. Jack, just give it up. Okay, both of you just like stop arguing. It's impossible to do this. You get a horrible grade on this. Now it's blame game, guilt traps. Sorry about that. I've just kind of accepted this isn't going to be any good. I'll still do it anyways. Hopefully it's really interesting. It's a really interesting topic, and hopefully that'll make up for the lack of presentation quality. Alright, so if you want to notice what's happening here, these little shapes are appearing and disappearing. What's actually going on if we click this window is we see these 3D shapes, and we have a plane that is crossing them. And using this plane, we can see cross sections of the shapes. So imagine where this plane is intersecting at any moment. That is what we'll be seeing. So these are the 2D cross sections of the 3D shapes. Now the one problem with this simulation is that this little stick man who'd be looking at them would not be seeing them like this, whereas we can see the inside, he would just be able to see the edges. So more accurately, it would be if you tilted it like this until you could see a one-dimensional view. But of course the display doesn't really do that very well. Alright, so we can have, you all understand, hopefully everyone understands that you can have two-dimensional cross-sections of three-dimensional objects, but what about three-dimensional cross-sections of four-dimensional objects? Now, if we do that, we can see part of a four-dimensional object, just like with the two-dimensional object, the 2D cross-section of the 3D, we saw that part of the 3D object, we saw it in complete accuracy, but we only had an infinitely thin slice of it. So if we do the same, 40, this is a 3D cross-section. Now I cannot show you the picture where I move the cross-section back and forth and you can see where it overlaps, because unlike last time, the cross-section itself is 3D. The whole is 4D, but I can move it along and you can see these shapes change. The shapes are not changing, we're changing, our perspective is changing. So our point of view is being moved along and we can see three-dimensional cross-sections of these four-dimensional objects. So this app is called 4D Toys, and I highly recommend it. You can play around with these things and really get a good feel for them. Alright, now that is probably, if you understand that, then that's like the hardest thing to understand. Once you understand that, it gets a lot easier to move on to other things. So could everybody just like say how much they understand it? Like maybe put a message in the chat. This recording, I'll have a recording of this that'll be available later, but I'll give it to all of you, but it's really hard to proceed unless we know everyone understands it. And if anyone has questions, just ask questions, because I'm super happy to clear anything up. And if you understand it, that's really great. Alright, everyone seems to get it. Alright, thanks. That's great. So we can move on. And let's move on. So, yes, there's one more way I know of representing these 4D shapes. You can use diagrams. Now, a diagram is great because it's accurate, and you can see the whole thing at once. And it can be on a 2D surface. But the one thing is that it's not a picture, it's just a diagram of how the vertices are connected. So, in a diagram, imagine you want a diagram Triangle. Let's start with something easy like a triangle. You would have the vertices and the edges, and you'd show how they're connected. Alright, glad everyone understands it. That's really good. So for a triangle, you would have the vertice here, you draw a little circle here, a little dot, and then you'd have another dot here and another dot here. And you want to show the relationship to how the dots are connected, so you draw a triangle. Now when we draw a two-dimensional shape, we can have it with complete accuracy, but when we draw a four-dimensional, we can't. So say I want to draw this tesseract as a projection. I think they're called orthographic projections, but I'm not sure. So let me see if I can find a picture. Let's just do one for a cube. So for a cube, one way to do it would be to have point here, 6 points for 6 vertices. I'm not sure you can see it. You can see them right there. And we connect them how a cube is connected. So there'd be the 6 faces of the cube. Those are the 2 squares, and then we would connect connections, and then we have a projection of a cube. So that doesn't look like a cube, but it is basically like a cube. And you can look up tesseract two-dimensional diagram, and you can probably find one like that. And so they sometimes look really complicated because they show all the